Oh, you are really study hard. We're diving straight into the world of machine learning using Python and the powerful Scikit Learn library. This is about harnessing data to build intelligent systems. So, what exactly is machine learning? Think of it as teaching computers to learn from experience, specifically from data. Instead of writing rigid code for every single scenario, we feed them data, and they figure out patterns and make predictions or decisions on their own. It's about automating insight extraction. Imagine recognizing handwritten digits, predicting stock market trends, or even recommending movies you might like, all without being explicitly programmed for each specific case. It's pattern recognition at scale, leading to data-driven decisions. Now, why Python? Well, it's not just hype. Python has become the de facto language for data science and machine learning, and for good reasons. Its ecosystem is incredibly rich. You have libraries like NumPy for numerical computing, Pandas for data manipulation, Matplotlib for visualization, and crucially, Scikit-learn for the core ML algorithms. Scikit-learn itself is a game changer. It provides a consistent and user-friendly API for a vast array of ML techniques. Plus, Python boasts a massive community, tons of documentation, and countless tutorials and resources. It's versatile enough for general programming tasks while being deeply powerful for ML-specific challenges. It lowers the barrier to entry significantly. Let's zoom in on Scikit-learn. This isn't some proprietary black box, it's open source, meaning anyone can use it, modify it, and contribute back. It's comprehensive, covering almost everything you need for standard ML tasks: regression, classification, clustering, dimensionality reduction, model selection, and more. A key strength is its consistent API. Whether you're using a simple linear model or a complex ensemble method, the way you fit the model to data and make predictions follows the same pattern. This consistency drastically speeds up development and learning. And it's built with efficiency in mind, handling large datasets reasonably well. To really work effectively with Scikit-learn, understanding some core concepts is essential. First, the estimator concept. Most objects in Scikit-learn are estimators. They have a fit method to train the model on your data and often a predict method to make predictions. Think of it as fitting the model to the training data and then using that fitted model to predict new data. Data is typically handled as NumPy arrays or efficient SciPy sparse matrices. Then there's model selection, which includes tools like train-test-split for dividing data, cross-validation techniques like k-fold to robustly evaluate performance, and hyperparameter tuning methods. Finally, preprocessing utilities help clean your data, handle missing values, scale features, and encode categorical variables, which are critical steps before feeding data into most ML algorithms. Let's talk about supervised learning. This is perhaps the most common type of ML task. The key here is that you have labeled data. What does that mean? It means for each input example in your training set, you also know the correct output or label. Your goal is to build a model that can learn the relationship between inputs and outputs so that when you give it new, unseen input data, it can accurately predict the corresponding output. Classic examples include regression problems, where you predict a continuous value like predicting house prices based on size, location, number of bedrooms, etc., or classification problems, where you assign a discrete label, like classifying emails as spam or not spam, or diagnosing an image as containing a cat or a dog. Contrast that with unsupervised learning. Here, the data is unlabeled. You only have the input features, no predefined correct answers. The goal shifts from prediction to discovery. You're trying to uncover hidden structures or intrinsic groupings within the data itself. Think of it as exploratory data analysis on steroids. Common techniques include clustering, where you group similar data points together, like segmenting customers based on purchasing behavior, or dimensionality reduction, which aims to simplify the data by reducing the number of features while preserving important information, often used for visualization or improving model efficiency. Let's make this concrete with a regression example, predicting house prices. Imagine you have a dataset of past house sales, including features like square footage, number of bedrooms, location, age of the house, maybe proximity to schools, and the final sale price. This is your labeled data. The price is the target variable or output. You could use algorithms like linear regression, which tries to find a linear relationship, or more complex ones like random forest regression. The trained model would then take a new house's details as input and predict its likely selling price. It's about finding the quantitative relationship in the data. Now for a classification example, spam detection. Here, you have a dataset of emails, and for each email, you know if it was marked as spam or not. Again, this is labeled data, but the output is a category, not a number. You might use algorithms like naive Bayes, which is surprisingly effective for text classification, or support vector machines. The model learns from the features of the emails, perhaps the words used, the sender's address, the presence of certain keywords, and so on, to classify a new incoming email as either spam or not spam. It's about drawing a boundary in the feature space. Let's look at an unsupervised learning example, customer segmentation. Suppose you run an online store and have data on customer purchases, browsing history, demographics, maybe website interactions. This data is typically unlabeled. Using clustering algorithms like k-means or hierarchical clustering, you can analyze this data to automatically group customers into distinct segments based on similarities in their behavior or characteristics. For instance, you might identify a segment of high-value, frequent buyers, another segment of bargain hunters, and yet another of occasional visitors. These segments allow for much more targeted marketing strategies than a one-size-fits-all approach. Building a successful ML model isn't just about picking an algorithm. It's a structured process. First, you must clearly define the problem you're trying to solve. What question are you asking the data to answer? Next comes data collection, gathering the relevant data. Often this is the most time-consuming and challenging part. Then, crucially, data pre-processing. Raw data is rarely ready for modeling. It needs cleaning, transformation, and preparation. After that, you move to model selection and training, choosing appropriate algorithms and fitting them to your prepared data. Finally, evaluation and deployment. How well did your model perform? Did it generalize well to new data? And if it's good enough, how do you deploy it into a real-world system? Let's emphasize data pre-processing. It's often called the unseen hero of ML projects. Why? Because raw data is almost never clean. It might have missing values, outliers, inconsistent formats, or irrelevant features. Handling missing data, deciding whether to impute or remove it. Feature scaling, making sure all features are on a comparable scale, which is vital for many algorithms like SVMs or distance-based methods. Encoding categorical variables, converting text labels like red, blue, green into numerical representations. And sometimes, feature selection, identifying and keeping only the most relevant features. Neglecting pre-processing can lead to poor model performance or instability. Investing time here pays huge dividends. Once you've trained a model, how do you know if it's any good? That's where model evaluation comes in. We need quantitative metrics to judge performance. For classification tasks, accuracy is common, but it can be misleading if classes are imbalanced. More nuanced metrics like precision, recall, and the F1 score provide better insights into the types of errors the model makes. For regression tasks, mean squared error, MSE, measures the average squared difference between predicted and actual values, while R-squared indicates the proportion of variance explained by the model. Crucially, we often use cross-validation techniques like k-fold to get a much more reliable estimate of how well the model will perform on unseen data, rather than just relying on a single train test split. Most ML algorithms have parameters that are learned from the data during training, but they also have hyperparameters that you, the developer, set before training begins. Examples include the learning rate in gradient descent, the number of trees in a random forest, or the regularization strength. Getting these right is crucial. Too few trees and the model might underfit, too many and it might overfit. Techniques like grid search systematically try every combination of hyperparameters within a specified range, which can be computationally expensive. Random search offers a more efficient alternative by randomly sampling parameter combinations. The goal is to find the optimal hyperparameter configuration that yields the best performance on validation data. While Scikit-learn is the powerhouse for core ML algorithms, it rarely works in isolation. It's part of a larger, interconnected ecosystem. Pandas is indispensable for data manipulation and analysis, handling data frames efficiently. NumPy provides the fundamental array structures and mathematical operations needed for numerical computations. Visualization libraries like Matplotlib or Seaborn are crucial for exploring data and communicating results. And Jupyter Notebook provides an interactive environment for coding, visualizing, and documenting your entire ML workflow. Together, these tools form a complete toolkit for building, evaluating, and deploying machine learning models. In conclusion, Scikit-learn is a cornerstone library that makes machine learning accessible and practical for professionals across various domains. It streamlines the development process, offers a wide range of algorithms, and integrates seamlessly with the broader Python data science ecosystem. It empowers you to tackle diverse problems, from simple predictions to complex pattern discovery. And importantly, it's continuously evolving, ensuring it remains a vital tool in the rapidly advancing field of machine learning.